So yesterday I formulated the Farrell-Jones conjecture, and it involved this equivalent homology theory of Davis and Luck. And the main goal for today is to give a definition of this in terms of K-theory. So we're going to define this as the K-theory of some additive category. Okay, and if I say K-theory of an additive category, I always mean together with the split exact sequences, right? I mean, no choice of further exact sequences. We always use the split exact sequences in my talk. Okay, but before we start with this, I wanted to add one thing, that this discussion about group rings can always also be formulated in terms of additive categories, and we can even allow twists. So we start with an additive category and a group acting on it by functors, and then we can form a group ring, and we can even twist it by this isomorphism. So let me spell this out. So the objects of alpha G are just the objects of A, and the morphisms in the bigger category between two objects are, as in the group ring, finite linear combinations. Finite, where now the coefficients are morphisms in A from A to B, and if we have a twist, then we need to take this into account. And at G, the coefficient phi G goes from G of A to B. So this is in A. Okay, and composition works as it does in twisted group rings. I guess right here, put the composition. U. Okay.
Does G acting on A mean that means it acts
Yeah,
on a set of objects on every single object?
No, it's supposed to mean it acts by functors on this category. And it acts strictly. So if I compose the functor for G with the functor of H, I, on the nose, get the functor for G times H. Okay? And then we can do sort of the same thing with any additive category as our coefficients, and maybe even, if we like with a twist. Okay. And then another thing I wanted to get out of the way. So I'll need metric spaces, and whenever I have a simplicial complex, I'll have to use some metric that sort of comes canonical from the simplicial complex. And one way to do this is using an L1 metric, where a point in a simplicial complex is a linear combination of vertices where the coefficients are positive and add up to 1, and then I can define the distance just by applying some norm to the coefficients here. So in this case, okay, so whenever we'll encounter simplicial complex, I'm always going to use this metric, to have a canonical metric around. Okay. And then so the key tool to construct this category is called controlled algebra. So
that's what you do on the simplex, and then you
no, I mean every point in a simplicial complex.
So it's bounded by 2, this metric.
Yeah. I mean, right. Okay, so I should have said this. So you often, right, we like to think this is the universal cover and it should reflect the coarse geometry of the group or something. But here I'm only interested in the local right? I'm going to be interested in small numbers, and so locally it works out fine. That's all. Yeah, that's a good point. Okay. So again, we start with an additive category, and we'll couple it to a metric space, and then define in the first version. Oh. Yeah, so mostly I'll spend my talk defining additive categories, I think. So this one is already the second. So given an additive category in a metric space, I can add a little more structure to A as follows. So I'm going to say the objects are triples, where S is some finite set. Pi is a map from S to our space X, and A is a map from S to X. Okay, so all we really have is a finite collection of all we really have here is a finite collection of objects in A, and for each object we also have a point in X. Right? That's what it's supposed to be. Okay, and then morphisms are just going to be matrices. So a morphism from one guy to another guy is given as a matrix of morphisms in A, right? So this is the entries are morphisms in A. Okay, so not much happened because this category is just going to be equivalent to A, an S pi A. We can just send to the sum of the S's, and then morphisms were really defined to be just morphisms over here. Okay, so, but the advantage is that we have a little more structure on morphisms because we have this metric on X, so we can ask how much does the morphism move with respect to X. Okay, and we have the following definition. So if I have a number epsilon, we say a morphism phi is controlled with respect to this epsilon if it satisfies the following condition. So whenever, so I have two, right? Two of the summons corresponding to S and S prime, and I look at the points I get in X, and I take their distance in X, and if they're far away from each other, meaning further than epsilon, then we require that the corresponding matrix entry is 0. Okay? So we've now sort of we can look at sort of matrices that are close to being diagonal matrices, because the entries that are non-zero are close to the diagonal in the sense that the corresponding indices are close when measured in X. Okay, and this might look a little artificial, but it comes up quite naturally in topology. So let me do the following example. So let's say X is a finite or compact simplicial complex, and I claim that then the simplicial chain complex of X is canonically an element in such a category where we use, say, the category of finitely generated free Z modules. Okay, namely, so we need a set for each, let's say n here. Right? So for each n, I need a set, and the set is just going to be the n. So as n is going to be the n simplices of our complex. Next, I need a map from the n simplices to my space. But the n simplex itself is already a subset here, so I just need to pick a point in there so we can map an n simplex to some chosen point in the simplex, and it's natural to choose the barycenter. And then, I mean, the simplicial chain complex has as a basis exactly Sn, right? So we'll just need one copy, one free summand for each of these simplices. So the map from Sn to the objects of finite general free Z modules just sends every sigma to the rank 1 module Z. Okay?
Can you repeat what F said X was?
Yeah.
Just say it.
Okay. Okay, and also this condition that things satisfy such a condition also comes naturally up in this context. Namely, we can look at the boundary map right, which will, I mean, map if I have a simplex here, I get a contribution here for all of the n-1 simplices that appear as a face of the corresponding simplex here. So we only get a non-zero entry if we only move by the size of a simplex. Okay, and if we don't like the size of a simplex, if the size of simplices is too big, then we can subdivide our simplicial complex to make the simplices smaller. Okay, so after subdivision, we can always arrange for the n right. Now I take the simplicial complex of a suitable subdivision of X, and then the boundary map will be epsilon controlled, right? Where the precise n depends on the epsilon I'm using. So this is in right? I'm not going to change X. I'm not going to change the metric on X. I'm only going to subdivide the simplices. Yes? Pardon? No, that's exactly why I wrote it carefully. So the subdivision we only apply to the simplicial chain complex, right, to make the simplices smaller. But we don't want to change the metric. If we also change the metric, then of course we didn't make any progress. So I kept the X here. Okay? Good. Okay. Okay, there is sort of a more topological version of this theory, and I want to talk a little bit about this. So we don't talk about the singular chain complex or modules over a space, but the spaces themselves. So I take two simplistic complexes and a map. I'm going to require its homotopy equivalence. And then we can make a similar definition as over here. We said a morphism in this category is epsilon controlled. We can say this homotopy equivalence is an epsilon homotopy equivalence. And we're going to measure this over y if we find a homotopy inverse and homotopies. So H should go from okay, so far I've just spelled out that G is a homotopy inverse to F, and then the epsilon comes in as follows. So we require that our homotopy is not supposed to move very much from the point of view of Y. So this means if I fix a point in Y, and similar, we have a requirement for points in X. So I'm going to look at what does the homotopy do to a point, let's say starting Y. What does the homotopy do to a point in Y? Right, so we get some path in Y. And we require that the path doesn't move much, so we require the diameter of this path is less than epsilon. And similar, we do this with the other. The other homotopy, only now that that's in X, and to get back to Y, we can simply apply F. Okay, and then, so this is another way to say that a homotopy equivalence is not very complicated, right? I mean, we had simple homotopy in Andreas's talk, and a theorem of Quinn is that if epsilon is sufficiently small, then this sort of easy or simple homotopy is in fact simple in the sense defined yesterday. Okay, so there's an epsilon such that all epsilon homotopy equivalences are simple and can then build by this combinatorial process of collapsing and extending cells. Okay. And maybe I would like to point out that this already tells us some connection about this epsilon business and homology, right? Because, I mean, what does it mean for a homotopy to be simple? One way to prove it is to prove that the white-hat torsion in the white-hat group should be 0, okay? But, I mean, the white-hat group is the quotient of K1 by the trivial units, but a fancy way to say this is Right? It's the quotient by the image of the assembly map, right? H1 of BG with quotient K of Z. That's exactly the trivial units. Okay, so this theorem says if my homotopy is an epsilon homotopy, right, then the corresponding element, which is first defined here, vanishes over here. In other words, it comes from here. In other words, it comes from a homology class. Okay, and that's the general principle. We can use this epsilon business to produce homology classes, but a priori there's a difficulty, right? We would like to say it's okay, we need small epsilons for this theorem to work in order to get homology classes, but this is of course not well behaved with respect to categories, because right, we have if phi and psi are epsilon controlled, and then if I multiply the two matrices, if I multiply two matrices that are sort of supported in the neighborhood of the diagonal, it will still be supported in the neighborhood of the diagonal, but the neighborhood gets a little bigger. So, and the composition is just 2 epsilon controlled. Okay, so we need some trick to get around this to actually get a category. Okay, so right, the solution would be here to try to take some sort of limit where epsilon goes to 0, then 2 epsilons will also go to 0. Okay, so the problem is then, how can we take some sort of limit? And there's a very nice construction that does this with a little trick and a shift as follows. So I'll need to define more categories. The next one I'm going to call O, depending on the metric space and still an additive category. So here I need to tell you what objects are. And again, there as before, we start with a set, but S is no longer finite. And our map is now a map to a product. Right, so we have a coordinate in X as before, and then a coordinate in N where we kind of try to take the limit as N grows. And then for every element in S, we need an object in A as before. Okay? So now S is no longer finite, and this means I'll have to add some finiteness conditions on these maps. So the condition is simply that if I look at the preimage of one slice here, I fix the entry in sort of the formal direction N, then I want it to be finite. Right, so we can think of as S being many finite sets, they all map to X with maps that change as I increase N. Okay, and morphisms. Are again matrices. Okay, but now I want to build in this notion that as N increases, we get smaller and smaller epsilons, and this we do as follows. Actually, before I need a technical condition. So first of all, I don't want morphisms to move too much in this n direction. Right? I have to allow them to move, but not too much. So I'll only allow them to move by a bounded amount. So I'm going to say there is an alpha depending on phi, such that if the distance in n is too large, then the matrix entry is 0. Okay, and then the condition that forces things to become small is as follows. So if we fix epsilon, then we want there to be an n0 such that past n0 this epsilon condition is satisfied with respect to x. Okay, so we're going to say if we're past n0 with respect to the projection to n, and it doesn't really matter whether or not I use s or s prime here by the first condition. Okay. So if this is, and if the distance in x of the projections to to x is large, then again the matrix entry is 0. Okay, so let me maybe Pardon?
What do we lose if we just take x?
We'll take x to be a point later on, maybe. I mean, we'll get another, right, the looping. Yeah, I'm creating space for the picture. Okay, so here is x, which maybe is compact, maybe not, and the other direction is n. Okay, and now I'm gonna, so if phi ss prime is non-zero, then I have sort of the point pi s and the point pi s prime, which maybe is here. And here it's a prime. And I'm going to draw an arrow to indicate, right, that we have a non-trivial matrix, a coefficient going from this point to this point. Okay? And now we have infinitely many of those, but by the first condition, they only accumulate as we go to infinity, right? In a finite range, there are only finitely many. And then the first condition about the alpha means that if we look at the length of these arrows with respect to the natural numbers here, I mean, that's bounded by alpha, right? So we can move like this, or like that, or we could not move at all, or we could do something like this. But it's all, I mean, we can't spread out in this direction. And then the second condition says, as I move further to infinity here, I mean, the arrows don't necessarily get short, but they kind of get horizontal, right? I mean, the start and the end coordinate with respect to x have to be nearly the same, because I mean this is exactly this difference, right? And we just stipulated if this distance is large, then the entry is non-zero, and I wouldn't draw the arrow. Okay. So as we go out to infinity, the arrows look more. I should have put in the other order. Look more and more horizontal. Okay. So they become local in x as we move to infinity. Okay. And then we just have to quotient out by sort of the stuff in the beginning. And a way to do this is as follows. So we're going to look at a subcategory that I'm used to be calling as T, where we in addition require that S is finite. Okay, so this is a full subcategory of what we had before. But of course, this is again a category that's just equivalent to A. Right now, if it's finite, then the conditions are really meaningless, right? If for the morphisms, and we can just sum up and get back an object in A. Okay, and this is then an instant. So this is an instant of what Chuck talked about in the previous lecture of a Karoubi filtration, and we can form the quotient okay, which in this case has an easy definition. So let's get the definition. The objects are the objects of the larger category, so we don't change anything. And the morphisms, so hom in the quotient category between two objects, those are the morphisms we had before. Well, we're going to introduce an equivalence relation where f is equivalent to g if and only if f minus g factors over some, how do I call it? Let's call it u in the subcategory, right? But in our case, in the case of these, I mean, this definition we can always give as a quotient category. But in our case, it is a very easy description. Namely, here I should have written phi and psi because I used phi's and psi's before, right? In our case, this happens exactly if phi s prime is the same as psi s prime for all but finitely many s. S and s prime, right? Because this t stuff stays in a finite region, then by this condition about the alpha, morphisms move only a little bit out. So anything that factors over something in this finite region only affects a finite number of morphisms, a finite number of these arrows, and those we can just forget, right? So what remains in this quotient category is exactly this picture, but only sort of the germ as we go to infinity, right? The arrows that are large with respect to x, we can always forget. Okay, so this category here, D, it achieves exactly this goal. It kind of implements this idea that we wanted, I erased it now, right? Wanted epsilon control for arbitrary small epsilon, right? And that's true in here, because every morphism in here has a representative, because I can forget everything that's too large, that is epsilon controlled with respect to x, right? So over x, the morphisms don't move much. Okay, and this is then responsible for the following theorem. put this maybe here. Of Eric Peterson and Chuck Weibel, namely the K-theory of this category is the homology that we're after in the non-equivariant case. Okay, we take the K-theory spectrum of A, and we get a homology theory, and it is implemented as the K-theory of this additive category. The only price we had to pay for this trick of involving this formal or this limit direction n is that we get a shift in degrees. So it doesn't work out quite perfectly. Right? The zeros homology ends up being K1, and so on. So there's a shift. Okay, and to show you the shift, I'll do the computation of this in the case where x is a point. Okay, so right, if x is a point, then all that remains is this. I mean, the epsilon condition is trivial because over a point, nothing can be different, and we only have this alpha direction. So we only have n, no longer x, and the condition is in the n direction. We're only allowed to move a finite distance. Okay, so let's compute the value on a point. And we'll start with computing not d, but the thing we defined before we took the quotient, this O guy, right? Okay, and the claim is this doesn't have any K-theory because we can swindle. Okay, and this works as follows. For any number n, we'll just look at the map on our, I guess I can define it on, I mean x is a point, but never mind. I can define it on x times n, and it just shifts to the right. So fn of x comma k is, we leave the x coordinate alone and shift the n coordinate by this number n. Okay, so we shift to the right, and then we obtain a functor on our category but we only change the way we think of our objects as being distributed over x times n, right? So we're only going to change pi by applying this map fn. So okay, so in this picture over here, what we would be doing is we move every guy a bit to the right. Okay. And since this means that we leave every finite region, right, because eventually n will be too large, we can add up all these fn's. So the sum of the n's is well defined and is the swindle. And it's the Eilenberg swindle we needed to conclude that this category has no case theory. So let's stop for a moment. Where did we use that that we were over a point here? Well, if we would try to do this over an interesting x, then we would keep moving this arrow to the right, and it would never get shorter in the x direction. Okay, so we can only work with this. So the swindle only works. Right, this sum is only well defined on morphisms if we're over a point. Right, otherwise it doesn't make sense. Okay, so over a point we get nothing from this O guy, and then we have the Karoubi filtration, which gives us a long exact sequence in K-theory of the T guy, but we argued T is just equivalent to A.
Sorry, how exactly do you use this swindle?
Hold on for a second. Okay, what was the question?
What exactly is the argument now? Now that we have this function?
Oh, well, I mean, this is an Eilenberg swindle. So what happens is the identity plus this big sum is isomorphic as a functor to the sum itself via, right, each of the fn's is isomorphic to the next one, because we can, again shift by one, right? We just shift by one to the right, and then that's the Eilenberg swindle. Better? Okay, good. Okay, and now we get a long exact sequence in K theory, right? And at this point we're going to use non-connective K theory, so we don't have to worry about anything happening at K0, right? We really have a long exact sequence. This one doesn't have any K theory, so this map is an isomorphism. Okay, and alternatively, this would be a way to define negative K theory, because in particular what we wrote here is K minus 1 of A is K0 of this guy. Okay, but then since we use non-connective K theory, we would really have to replace this with its idempotent completion. Okay. So that's the computation on a point, and then we need to show, right, that it is in fact an homologous theory. I'm not going to do this, but it in the end comes also out of Karoubi filtrations. So this theorem that we get long exact sequences from Karoubi filtrations is the key step to get exact sequences in this theory. And then to prove that it's homotopy invariant is another version of this kind of swindle. Right? Yeah. I mean, to prove that the theory is homotopy invariant, you need to show something about x times an interval 0, 1, and then you try to swindle in the direction of this interval. Okay. Pardon?
What's the statement? How do you...
I didn't prove the theorem. I just proved the theorem in the case where x is a point.
Yeah, but how does it prove the theorem that just got x to the point?
Right? I mean, what was... All right, this was the thing that the homology theory we got from... Right, so for... Pardon? Sorry, we don't know, but on a point, it was designed to be the K theory of the category, right? Yes, okay, I should have said that. Okay, so this is the theory that comes up in Chung's conjecture, where we didn't allow for any isotropy. But if we want to allow isotropy, then we need to get to the equivariant point of view. Okay, but with what I said in the beginning, this is actually now very easy. So now we think of a group acting on our simplicial complex, and let's ask for the action to be simplicial. Okay, and then we get corresponding actions first on this O guy. It's called the action alpha, but then also on the other categories, the quotient and the subcategory we had, in the finite one that we divided out. And we can simply form, okay, let me write down the action. Right, I need to define what is G applied to an object, and then on morphisms it's not going to do much. So we're not going to change S. We're going to change again our point of view, how we think about S being distributed over our space, x times n. So we just multiply with G in the x coordinate and do nothing in the n coordinate. And if we had an action on A, on A to begin with, we would stick it in there as well. Okay, and then we have the equivariant version of the theorem. And it says that now we get the Davis-Look theory with the same shift. In degrees. Okay, and that was what I set out as my main goal for this lecture. Okay, and I want to emphasize, I mean, even if one is only interested in Chung's conjecture, right, all proofs usually go through the Farrell-Jones conjecture in the sense that the cyclic subgroups, right, in this case it's only going to be cyclic subgroups. Cyclic subgroups are going to play a special role. So at some point there will be isotropy for the cyclic subgroups will have to appear. So usually, even if one is only interested in Chung's conjecture, one ends up having to prove the Farrell-Jones conjecture. So one ends up having to work with this category. Okay.
Sorry. So should we take this as the definition of this?
Well, I mean, the official definition of Davis-Look is a different definition. Okay, it's one that works in much more generality. You just start with a functor defined on the orbit category from the orbit category spectrum, then you can always form from this Davis-Look theory. But in this particular case of K theory, it has this incarnation, and that's the version or the theorem is useful in proving the Farrell-Jones conjecture, because now it is sort of, we can all work in K theory, right? We can try to, right? I mean, the assembly map, let's put this here. Right? The assembly map is now induced from this functor here. Okay, we have this functor that just projects x to a point. We need to put in the right x, this classifying space that we start with. And the claim is this map induces an isomorphism in K theory, so we can try to just come up with some way to go back. I mean, we won't quite define a functor from here to here, but we'll be able to define a functor to somewhere else, and then an isomorphism and invert some stuff. I mean, the way one usually, tries to prove something is an isomorphism if there isn't a direct inverse. There's maybe a zigzag and some inverses that we have to invert. But it's all going to be then in the language of K-theory, right? Going back is all formulated in terms of functors. Oh, that's this one. Oh, and then applying K-theory. Okay. Okay, maybe let's, okay, so the Farrell-Jones conjecture is for the right x, this projection map should be an isomorphism in K-theory. And that's the use of this theorem, and not necessarily that this is computationally helpful in understanding the right-hand side. I mean, if we want to compute this, then the point of view of Davis looks much more useful. Yeah?
So you have this map, which doesn't have anything to do with K-theory, right?
Which map?
The map on the D.
This map, yes, yeah, right. Yes?
Are there other theories for which?
Yes, of course. Good point. Since excellent point. So the Farrell-Jones conjecture, I only talked about K-theory. But really, for topologists, if we say K-theory, we also need to say L-theory, right? For surgery theory. And there's the same, I mean, everything I said has an analog in L-theory. In particular, Farrell-Jones also formulated their conjecture in L-theory. And then, again, this theorem, you just put an L here and an L here, and it remains true. Okay, and then L-theory talks about the obstruction groups in surgery theory, so it's even more important to the classification of manifolds. And then if you have both versions of the conjecture, in K and in L-theory, then a corollary is the Borel conjecture that states that spherical manifolds are determined up to homeomorphism by their fundamental group in dimensions at least 5, because this uses surgery theory. And that was one of the main motivations for Farrell-Jones to study and introduce these conjectures. Okay? And then,
Well, you said 2, why not many? I mean, why just...
well, okay, these are the two important examples where it originally was formulated, but then there are variants that can't quite be said in terms of this additive category language. So there's also you can formulate the Farrell-Jones conjecture in A theory. You can formulate it for pseudo-isotopies. Okay, but and then again, it has controlled kind of descriptions, but it's no longer this additive category that plays the role. But you could also ask, I mean, it is a very good question. What kind of properties does a functor need to satisfy, right, from say additive categories to spectra, in order for the Farrell-Jones conjecture to be something that has a chance? Okay, and so far for this theorem we haven't used much, right? Basically what we have used is this trick of Eilenberg swindles and Karoubi filtration. Those give us long exact sequences. If you have those two, you'll get this isomorphism. Okay, to prove this isomorphism, we'll need a little more. So this is maybe less easy to make explicit what is it exactly that's used. So this I'm only comfortable saying is going to work in K and L theory for certain groups. But otherwise, yes. Good point, thank you. Okay, so I've said what I wanted to say, but since I have a little more time, I'll go back to this statement I made about control topology of epsilon homotopy equivalences and discuss a little bit how it relates to this discussion. Oh, maybe before. I can give you if you want to play with the definitions and check that they work out nicely, you can check the following. So we could use, we can use the case of a free action, and then we can check that this isomorphism we had works. So we can use D X A with this, and on the other hand, we can use the quotient and not take the group elements. And then those two are equivalent as additive categories, right? And that the corresponding statement of on homology groups was something I asserted yesterday. Okay. Okay, so back to this notion of epsilon homotopy equivalences. So, right, to get the group involved, we have to lift to the universal cover. So then it lifts to an epsilon homotopy equivalence and G equivariant, where G is the fundamental group of both, since they're homotopy equivalent. And it's Whitehead torsion, which is the thing we need to compute to check that it's simple, is then, because of this epsilon assumption, an epsilon isomorphism in here, and then what Quinn really proves is there is an epsilon, depending on the dimension of f, such that if phi is an epsilon isomorphism, then its K-theory class is in the image of, so we have the group ring where the thing is defined to be in to begin with, but this is the same as free right, this gadget. And so that's an isomorphism. Maybe I should just leave this out. Okay, so then it's in the image of this assembly, the assembly map for X. And then in particular, it's 0 in the Whitehead group of that, right? Because that's the quotient by, I mean, sort of the terminal thing where we put in EG over here. Okay, and that's the way the theorem I had on the board earlier is proven. You prove an algebraic statement. If an algebraic gadget satisfies this control condition, then it is in the homology theory, and therefore it's trivial in the Whitehead group. And that we get from it being an epsilon homotopy equivalence and the geometric assumptions to the corresponding algebraic assumptions just follows from the formulas that Andreas gave us in his talk. I mean, you really write down just the formulas. Okay, thank you.
What does it mean if the Whitehead portion is an epsilon isomorphism?
Yeah, I thought I didn't give the careful definitions at that point, right? So in this here, I say phi is an epsilon isomorphism by definition if phi and its inverse are epsilon controlled. Okay, that's without the group action. And then here I need to talk in this setup, and then it's slightly different. So we can say the guy in here has this form. It's because we took this group ring here. It's a finite sum over G, and then we require that whenever G pi S pi prime S prime is bigger equal to epsilon than the corresponding matrix coefficient for the corresponding G is 0. Okay, that's to say, so this is an epsilon, is epsilon controlled? Is this here? Sorry, right. Such a gadget is epsilon controlled if this condition is satisfied, right? I mean, you have to put in the G here because of the way things are set up, that the G acts on X tilde. And then to be an epsilon isomorphism is the same as here, if the gadget and its inverse are both epsilon controlled. But in Andreas's talk, from the formulas he gave, you get explicit, more or less explicit phi G's, right? And if the F here only moves a bounded amount, then the phi G will have the phi G's will have the corresponding control condition.
You need some sort of a sufficiently small epsilon for that assertion in the upper left. Because not every epsilon, the first two.
Oh, this one. Yeah, I wasn't quite sure. I thought maybe not, but.
Well, if you take a small figure 8, for example, and you take the involution which switches the factors, and if epsilon is too big.
Yeah. Okay. So you're right. So if for small. Thank you. And this is very much related to exactly this thing, right? Because that's not going to be true if we put instead of D, we would put O. It only works on D because because then everything is small and that allows you to lift. So it lines up nicely with this.
More questions? Okay, then